Okay, so this is our 35th lecture session and we'll continue our discussion on the turbulent 5 flows. So in the previous lecture we discussed that when we are having the turbulent flow near a solid boundary, then we are having the occurrence of three different regions. One is called as inner layer, where we are having the viscous dominant flow, and then we have some outer region where molecular viscosity does not influence the flow, and then we have some overlap region where both the inner layer and the outer layer are merged together, and then we are having some logarithmic variation of the velocity field. Okay, one important conclusion we found that the inner layer, whatever the inner layer law is there, that is only applicable up to y plus nearly equal to 5, and for the extreme outer layer portion, our all the actual experimental velocity profile comes very close to the logarithmic profile for with a single exception of flow with strong increasing pressure gradient. Okay, so that is the only condition for which this logarithmic actual experimental profile is not coming close to the logarithmic law. So what we will be doing, we will be making an assumption that for entire boundary layer zone across the wall, we have nothing but the logarithmic variation of the velocity field. Okay, and by using this logarithmic law for the velocity field, we will try to deduce the formulation of velocity field corresponding wall shear stress, and then determine relation of friction factor for the turbulent flow conditions. Okay, so we can see in the subsequent discussion. So now what I have done, I have considered a circular pipe cross section, and in this circular pipe cross section, say this is my variation of velocity, variation of radius r from the center line of the pipe. Then of course, if I am referring to this point, so when we consider the logarithmic velocity profile, in this logarithmic velocity profile, basically this y is nothing but distance of the point at which we are interested in finding out the velocity, the distance of this particular point from solid wall. Okay, so whenever I will be writing the commensurate form of this velocity profile for the case of pipe flow, I have to consider this equivalent distance to that of y. So it means that distance I have to measure nothing but from the solid boundary of the pipe. Okay, so if I do so, in this pipe flow, my outer radius of the pipe is capital R, and the point which I am referring to is small r. So with reference to wall, how much distance I have? So with reference to my wall, the point at which I am interested in finding the velocity, the distance is capital R minus small r. Is this point clear? Because logarithmic velocity profile, whenever we have obtained, we have measured the distance with reference to the wall. Okay, and in my pipe, this small r is measured from the center line of the pipe. If r is radius, then capital R minus small r will be the distance of arbitrary location in the radial direction from the solid surface of the pipe. Okay, by considering this assumption, I can write my variation of velocity in radial direction divided by u star, where u star is nothing but wall shear stress divided by rho and square root of this. Okay, so ur by u star is equal to 1 by kappa. Kappa is constant. Log of, in place of y, I have got r minus r, capital R minus small r, times u star by nu plus b. So this is the nothing but velocity profile in my turbulent flow for a smooth pipe, for a pipe. Okay, so in case of laminar flow, what was the velocity profile equation? U equal to u max times 1 minus small r square by capital R square. Okay, so the equivalent velocity form for turbulent flow is nothing but u by u star equal to 1 by kappa ln of r minus r u star by nu plus b. So it means that we will be having nothing but the logarithmic velocity variation across the cross section of the pipe. Okay, now if I have to find the average velocity, how to find out the average velocity? Can you tell me? to find average velocity, what I can do, I can write my average velocity at any cross section, that will be nothing but equal to flow rate, volumetric flow rate per unit cross sectional area of the pipe. Okay, so area of the pipe is 1 by pi r square, and volumetric flow rate can be written as u times dA, integral of u times dA with integration from 0 to capital R. Okay, so u will be nothing but velocity at any arbitrary location u r, and corresponding to that location, what is my cross sectional area? Cross sectional area will be, if I consider that I have a small ring across the cross section of the pipe, and this particular ring is at radius r and it is having thickness dr, then my cross sectional area at which my velocity is ur, this cross sectional area dA will become nothing but 2 pi r into dr. Is this point clear? So that's why what I have done this integration from 0 to r, and this is ur is nothing but u star times 1 by k ln of r minus r u star by mu plus v, and in place of area I have got 2 pi r into dr. Is this point clear? Okay, now if I do this integration and substitute the limits of integration, I will be finding final formulation as 1 by 2 u star times 2 by k ln of r u star by nu plus 2b minus 3 by k. Okay, so this is the, over here, can you tell me what is V? V is nothing but average velocity. So average velocity, we have got this particular formulation, which was for a fully developed laminar flow. What was average velocity? It was nothing but maximum velocity by 2. Okay, so in case of turbulent flow, by considering the logarithmic velocity profile, my average velocity is coming out to be this value. Okay, so now this equation can be further simplified after substituting the values of k and b over here. Okay, so if you recall, k was nearly equal to 0.41 from the previous slide. You can see k is nearly equal to 0.41 and b is equal to 5.0. So if I now substitute the values of k and b over here, I will be getting my velocity profile as v by u star equal to 2.44 into ln of r u star by mu plus 1.34. Okay, is this one clear? All are clear with this idea? Now, from our earlier understanding also, we can write v by u star. This we have done from the, we have made analogy from the corresponding annular flow profile, laminar flow profile. Okay, so from the laminar flow profile, I can write that v by u star can be written as rho v square by tau w square root, and which comes out to be nothing but 8 into 8 divided by friction factor square root. Okay, so this is something which we have already done, while we have correlated the wall shear stress with velocity profile, particularly with the Wisbach equation for friction factor. Okay, so this is the generic formulation. Now, r u star by nu can be written in terms of 1 by 2 vdb by nu into u star by v. Okay, so this particular formulation, if I substitute back over here, then I can write that my r u star by nu is nothing but equal to half of Reynolds number into f by 8 power 1 by 2. Okay, now combining this equation, equation number 1, second equation, equation number 2, and equation number 3. Combining 1, 2 and 3, I will be getting one relationship for friction factor 1 by f power 1 by 2 is nearly equal to 1 by 1.99 log of, so here this is natural log of Reynolds number into, when Reynolds number is calculated based on diameter of pipe, into friction factor power 1 by 2 minus 1.02. Okay, so it means that in case of laminar flow, my Reynolds, friction factor was nothing but equal to 64 by Reynolds number. So that was when we considered the parabolic velocity profile. when we did the similar analysis by considering the logarithmic velocity profile, then my friction factor has become 1 by f power 1 by 2 nearly equal to this particular correlation, and this is applicable nothing but for fully developed turbulent flow. Is this point clear? So basically we did the similar analysis, but the only difference was that in case of fully developed laminar flow, the velocity profile was parabolic. Here velocity profile is logarithmic. Okay, is this point clear? So in place of 64 by Reynolds number, friction factor for turbulent flow is this one. Now Prandtl has further simplified this equation to modify the coefficients so that these modified coefficients comes more closer to the experimental data. Okay, so after the Prandtl's modification, this coefficient 1.99 has become 2.0 and this coefficient 1.02 has become 0.8. So I can consider this to be my main actual equation which shows the variation of friction factor with Reynolds number for turbulent flow. Okay, so theoretically relation is coming out this like this, but Prandtl has slightly modified the coefficients so that the coefficients are taking the form which are having more close accuracy with the experimental data. Okay, so this is the equation which Prandtl has actually given. All are clear up to this point? So it means that if I have to find the pressure drop or head loss in a turbulent flow in a circular pipe, what I have to do, I have to first solve this friction factor equation. Okay, then I will be able to find out the friction factor. Once I know the friction factor, then after that I can actually, what I can do, I can substitute this friction factor into the equation of the head loss FLV square by 2GD, and I can calculate the corresponding value of the head loss for turbulent flow. Okay, but one important point we have to note, on the left hand side also I have friction factor in this equation, and in the right hand side, particularly within the log term also I have this friction factor in this equation. Okay, so it means that this particular equation gives me the formulation of friction factor in nothing but an implicit way. Okay, so I cannot explicitly, by just substituting the value of Reynolds number of the flow, I cannot find the value of f. Okay, so this f is appearing in this equation in an implicit manner. So what I have to do, I have to try some advanced mathematical tools or some iterative procedures in order to find out the value of f from this equation. Is this point clear? Okay, because f is appearing in left side as well as log of right side. So that's why this equation was bit lengthier for doing the routine calculations of pressure drop. So what people have done, particularly student of Prandtl Blasius has tried to do some experiments, and based on his experimental data, he tried to fit a functional form for friction factor purely in terms of the Reynolds number of the pipe, so that I can get, or we can get, nothing but the explicit value of friction factor, which will be easy from computation point of view. Okay, so Blasius experimental data shows that friction factor for fully turbulent flow inside a circular pipe can be made equal to 0.316 times Reynolds number, which is calculated based on diameter of pipe, power minus 1 by 4. But this particular data is only fitting in the range of Reynolds number 4000 to 10 to power 5. Okay, so it means Blasius, whatever the equation Blasius has given, that equation is not applicable for entire range of turbulent flow, but it is applicable for very specific data set within the specified range of Reynolds number. Okay, so that's why one more equation was proposed later on, and this was proposed by some other scientist. At the moment I can't recall the name, and this equation is 1.8 times log of Reynolds number d by 6.9 and whole power minus 2. So this particular equation is applicable for entire range of turbulent flow. Okay. So this is applicable for complete range of the turbulent flow. Is this point clear? So it means that once I have these two equations, particularly the second one, by just knowing the Reynolds number, I can directly calculate the value of friction factor. Okay. So once I have friction factor, I can calculate head loss, and head loss for a horizontal pipe where elevation is not changing will be simply equal to delta P by rho G. Okay, because delta Z will be 0 for that case. So that comes out to be F into L by D, V square by 2GD, and F, if you substitute value of F from Blasius correlation, so Blasius correlation tells 0.316 into mu by rho V D power 1 by 4. Okay. So if you substitute this from Blasius correlation, you will be finding that delta P is proportional to V power 7 by 4 for turbulent flow. And what is V power 7 by 4 for turbulent flow? It is 7 by 4 is nothing but equal to 1.75. Okay, so it means that for turbulent flow, my pressure drop is directly proportional to velocity power 1.75. Is this point clear? So that is something which we have seen in the previous section also, while we were talking about the dimensional analysis. At that time also we have fitted data into the dimensionless variables and we found this correlation. Okay. One important point you can see over here, when I present this data of delta P, so this is equation of delta P in terms of velocity. Now if I replace this velocity with flow rate, then what I have to do, Q by cross sectional area whole power 7 by 4. Okay, so this will modify this constant pi. So of course the value of constant is modified from 0.158 to 0.241, plus in place of velocity I will be getting Q power 1.75, and along with that the power of diameter will also be modified. Okay, so power of diameter over here is coming out to be minus 4.75. So now we have one very important conclusion over here, particularly from the application point of view. Okay, so if you recall your laminar flow equation, what was laminar flow equation? 32 mu LV divided by rho G D square. Okay, rho G D square. So it means that in case of laminar flow conditions, delta P is inversely proportional to square of diameter. Okay, delta P is inversely proportional to square of diameter. On the other hand, for turbulent flow, delta P is inversely proportional to diameter power 4.75. It means that if we have a pipe and in that pipe I have some Q amount of flow rate, for same amount of flow rate, if I increases the diameter of the pipe, okay, under the laminar flow conditions, my reduction in pressure drop will be less, but in turbulent flow conditions, by increasing the diameter of the pipe, reduction in pressure will be more. Okay, so typically you can see that if you increase diameter from D to 2D, so how much change will be there? 2 raised to power 4.75. How much is this value? 2 raised to power 4.75. So for a given flow rate, if we simply 26.9, so almost 27. So it means that for fully developed turbulent flow, for a given flow rate of the fluid, if I simply increases the diameter of the pipe by 2 times, my pressure drop will be decreasing by 27 times. Okay. On contrary, in case of laminar flow, where delta P is inversely proportional to only D square, their pressure drop will be decreasing by 4 times only. Is this point clear? So this is very important point, that in case of turbulent flow, my pressure drop on doubling the diameter reduces by original pressure drop divided by 27. Okay, so 1 by 27 of the original pressure drop. But in case of laminar flow, it will be only becoming 1 by 4 times of the original pressure drop. Okay, so it means the influence of changing the diameter in case of turbulent flow is more significant. Okay, so if you are designing, as a designer, if you are designing some pipelines for industrial applications and it is desired that we should have less pumping power and flow condition is turbulent, you can simply propose to increase the diameter of the pipe, because that will be decreasing the pressure drop by a significant amount. Okay, is this one clear? So this result is very, very important from the application perspectives. Okay, now we can talk about velocity profile in laminar and turbulent flows. So we know that in laminar flow our velocity profile u by u max is equal to 1 minus small r square by capital R square. So that's why my velocity profile is actually parabolic. Okay. On contrary, in case of turbulent flow, if I calculate u max by u star, that comes out to be 1 by k ln ru star by v, or this gives me relationship between v by u max as something like this, okay, in terms of the friction factor. So one important thing which we want to compare over here is that in case of laminar flow, my average velocity is half of the maximum velocity. Okay, so there is a significant change in between the average velocity and the maximum velocity. On contrary, in case of turbulent flow, average velocity and maximum velocity are actually very close to each other. So these are almost comparable. So because of this, in this central zone, we will not be having significant gradient of the velocity, but majority of the gradient will be existing only near the walls. Okay, so this way, when we will be increasing the diameter of the pipe, what will be happening? The gradient near the wall will be only influenced, and in the center I will not be having more occurrence of the gradient. So that way I will be finding more reduction in the pressure head in case of turbulent flow in comparison to the laminar flow. Is this one clear? Okay, now comes very, very important point. So till now, whatever the value of friction factor we have obtained in the previous slide, here you can see the whole idea of this friction factor is only dependent upon Reynolds number. Okay, so it is not taking care of the roughness of the surface of the pipe. Okay, but whenever you will be going to the practical conditions, you cannot ensure the perfectly smooth pipes. But for laminar flow conditions, we already saw in the previous lecture that even if we have pipe roughness, because of the layer wise smooth flow of the fluid, the influence of roughness actually does not cause any effect on the pressure drop characteristics. But on contrary, in case of turbulent flow, because of the fluctuating components of the flow or fluctuating motion of the fluid particles, we will be having significant effect on pressure drop characteristics of the roughness of the pipe surface. Okay, so that's why this person was Nikuradse. So Nikuradse was another student of Prendtl, who performed significant experiments for estimating the effect of wall roughness on pressure drop characteristics. Okay, so what Nikuradse did, he has actually taken the grains of the sand particles, and these grains of the sand particles of different roughness he has glued on the inner surface of the pipe, and then he performed different experiments under the turbulent flow conditions in order to, both in the laminar and the turbulent flow conditions, in order to determine the values of friction factor. Okay, so typically you can see that this is the experimental data of Nikuradse. So here we have friction factor, and this side we have Reynolds number, and these all circles, these are nothing but experimental data. Okay, so you can see that in laminar flow conditions, all these circles are nothing but following our this relation 64 by Reynolds number. Okay, in case of turbulent flow, you can see this previous equation, friction factor, this 0.316 into Reynolds number power minus 1 by 4 or 1.8 log of Reynolds number d by 6 by 9 minus 2. Okay, if you plot these equations, so you can see these are two equations, one is this and another one is this equation. So these two equations are nicely matching with the experimental data when our roughness, this is epsilon by d. So epsilon is nothing but the absolute roughness and d is diameter of pipe. So epsilon by d is called as relative roughness. Okay. So when epsilon by d is less than 0.00099, then whatever the friction factor correlations of smooth pipe are there, these our experiments are giving, or experiments of Nicoradse are actually following these lines. Okay. Moreover, for roughness greater than 0.0099 to any value, you will be finding that at very high Reynolds number, the values of friction factor almost saturates and becomes independent of the Reynolds number. Is this one clear? At high Reynolds number, what is happening? These effects are actually saturating and becoming independent of the Reynolds number. On contrary, the deviation from the smooth correlations are observed for higher roughness at smaller Reynolds number. Is this point clear what I said? So, when your value of relative roughness is increasing, you are finding deviation from the smooth pipe surface is occurring at low values of the Reynolds number. When you are decreasing the value of relative roughness, then deviation from smooth pipe correlation is taking place at very high Reynolds number. But if you increase the roughness, then deviation is actually decreasing towards the low Reynolds number points. Is this one clear? So one important point is, basically we know that our y plus value of 5 is equivalent to the viscous layer. Okay, so this y plus value of 5, if I equate to the friction factor correlation, then I will be finding from here that y plus 5, which is nothing but becoming a function of Reynolds number, that is also having some connection to the roughness. If your y plus is small, so it means that your laminar sublayer will be occurring within the maximum roughness portion of the pipe. But if your y plus is large, it will be occurring beyond the maximum roughness portion of the pipe. Okay. So if y plus is large, it means it is beyond the maximum roughness portion of the pipe, then correlation of smooth pipe will be applicable up to larger Reynolds number. But if y plus is small and it is going above the rough portion of the pipe. Okay. In that case, if it is small and it is within the maximum rough portion of the pipe, then influence of laminar sublayer will not come into picture. That's why the deviation will happen at low Reynolds number from smooth pipe correlation. Is this one clear? What I am trying to say, let me show you in the visual manner also. Say this is my maximum roughness and this is my small roughness. Okay, and let me consider this line is corresponding to y plus nearly equal to 5. Here also this line will be y plus nearly equal to 5. So here you can see in the second case where my roughness is small, y plus is completely bounding the whole rough portion of the pipe. If y plus is completely bounding the whole rough portion of the pipe, my transition from smooth pipe correlation to the rough effect will occur at higher Reynolds number. Okay, extremely higher Reynolds number, because in this zone my viscous sublayer will be dominant. On contrary, in this case what is happening? Viscous sublayer is there dominant, but that is lying within the roughness. Beyond viscous sublayer also some rough portions of the pipe are protruded. Okay, so in this portion the effect of roughness has to be accounted sooner. So that's why this roughness effect is actually transferring towards the low Reynolds number upon increasing the roughness of the pipe. Is this point clear? Okay. Now, one important correlation is there. So we can define one value epsilon plus. Epsilon plus is nothing but epsilon into u star by nu. If epsilon plus is less than 5, then we can say that we will be having hydraulically smooth walls. So initially I told you hydrodynamically smooth pipe. So hydrodynamically smooth pipe for laminar flow exists always, but hydrodynamic smooth pipe for turbulent flow will be existing only when epsilon plus is less than 5. Okay, and if this condition of hydrodynamic smooth pipe is valid, it means I am referring to this second condition. If this second condition is valid, then I will not be having any effect of roughness on the friction factor. Is this point clear? Okay, if my pipe is hydrodynamically smooth, it means if my epsilon plus is less than 5, then of course I will not be having any effect of wall roughness on the friction factor. Is this one clear? When my epsilon plus is within 5 to 70, here I will be having transitional roughness. It means small effect of roughness will come into picture. That's why I will be having moderate dependence on Reynolds number and some dependence on the roughness. Okay. On contrary, when my epsilon plus is greater than 70, in this case I will be having the fully rough flow. So whole friction contribution will be mainly because of the fully roughness, and sub layers of laminar resin will be completely breaking because of the protruding rough portions of the pipe material, and I will be having flow as independent of the Reynolds number. So that is something which I am trying to show over here. So here you can see after this zone, particularly after this zone, at every Reynolds number my friction factor is becoming constant. So this is nothing but the zone of epsilon plus greater than 70. Okay, where the dependence of Reynolds number on friction factor has vanished and purely contribution has taken up by the roughness of the pipe. Is this point clear? And in this particular zone, which is from 5 to, so here this is the zone which shows epsilon less than 5. In less than 5 there is no effect of roughness. So correlation is identical to a smooth pipe. But in this particular zone, which is having value of epsilon plus from 5 to 70, in this zone we have combined effect of Reynolds number as well as the as well as the roughness. Okay, is this one clear? And particularly if you want to write friction factor, then ultimately it can be correlated with this particular correlation for the rough pipes. Okay, so this is for which reason? Epsilon plus greater than 70. Okay, so when epsilon plus is greater than 70, then you will not be having any dependence on Reynolds number. So friction factor will be simply becoming the function of the roughness of the pipe. Is this one clear? Okay, so these experiments of Nicoradze were very, very important in determining the effect of wall roughness on the pressure drop or the corresponding friction factor characteristics. Okay, but one issue was there. Nikuratse has created the artificial roughness by putting coarse grain particles of sand on the surface of the pipe. Okay, so it was later found that for certain range of roughness, particularly near the transitional regime, these coarse sand grains does not mimic the surface roughness values equivalent to that of the industrial pipes. Okay, so now our interest should be to go for the industrial pipes, because artificial surfaces are just from the point of view of understanding of the flow dynamics. Okay, but in reality, if you have to design some system, there you will be finding the industrially manufactured pipes. Okay, so that's why people have later on also performed some experimental analysis with industrially rough pipes. Okay, and to relate the pressure drop for or friction factor for such surfaces, a detailed diagram was given, which is called as Moody's diagram. So this Moody's diagram is basically based on the correlation of Colebrook. So Colebrook has done significant experiments and he developed this particular correlation. 1 by f power 1 by 2 equal to minus 2.0 log of epsilon by d divided by 3.7 plus 2.51 by Reynolds number f power 1 by 2. So this is the detailed correlation based on which a diagram is plotted, and this particular diagram is actually called as nothing but the Moody's diagram. So Moody's diagram is very famous diagram which is used for circular pipes, non-circular cross sections by doing some modifications in the diameter, and as well as for open channel flows. Okay, so if you have to consider the applicability of the Moody's diagram, it is applicable for both for three different conditions. Of course, for circular pipes, then for non-circular ducts also it is applicable by doing certain modifications in the parameters, and then it is also applicable for open channel flows. Okay, and you can see in the Moody's diagram, this particular line over here is for laminar flow, which is identical to our theoretical relation 64 by Reynolds number. This is the critical value of Reynolds number close to 2300. After this critical Reynolds number, I will be having some transitional zone, and particularly this shaded portion is considered as the critical zone, where exactly identifying the value of friction factor is actually very challenging. Okay, so in this zone, exact identification of friction factor is actually not feasible, and this is the transition zone, and after transition zone I have multiple lines over here. So bottommost line is for smooth pipe, and when I have these above multiple lines, these are nothing but corresponding to the different values of relative roughness for different values of epsilon by d. Okay, and on this Moody's diagram I have this one dashed line over here, and this dashed line shows the demarcation from, so this is basically epsilon plus greater than 70. Okay, so beyond this I have whole dependence only of the roughness, not of the Reynolds number. Okay, and this is one correlation which can mimic, this Colebrook's correlation can mimic the complete Moody diagram within the accuracy of 10 to 15%. But then one more modified correlation is proposed which can mimic the Moody's diagram with less than 5% of accuracy, and this is the second correlation. So there are two possibilities. Either you can use simply this correlation to obtain the data of friction factor if you know epsilon by d and Reynolds number, or you can refer to this Moody's chart. So most correct thing is Moody's chart. These correlations are developed to mimic the entire data of Moody's chart within certain range of accuracy. Is this one clear? So these are certain values of roughness for majority of the commercial ducts. So you can see if you are having material steel, iron, brass, plastic, concrete, etc. So which are the common construction materials for the ducts, and these are the conditions. If we have sheet metal, stainless steel, or galvanized sheet, so different types of conditions are there, and depending upon that you can see the corresponding value of the roughness within the uncertainty limits of this percent. Okay, so it means that if it is given to you that you have some pipe and it is made up of this material, then what you can do, you can simply refer to this table and you can choose the value of epsilon by considering this table. Okay. Now, once we know this data of head loss, friction factor, velocity, flow rate, then what we have to do, we have to now solve the different practical problems. So one practical problem can be where it is given to you that the fluid which is flowing in the pipe has density rho, viscosity mu, and diameter of the pipe is d, velocity of either velocity or flow rate of the fluid is actually given to you, and length of the pipe is given to you. So in that case, what you need to do is you need to calculate the pumping power. So for calculating pumping power, of course, you have to determine head loss. So this is a straightforward problem. Okay. Then second problem can be where, of course, fluid will be given, which fluid is flowing. So if fluid is given, it means density and viscosity are known to you. Okay. And diameter of the pipe is given, length of the pipe is given, diameter of the pipe is given, flow rate is given, and also it is given that how much is head loss. And corresponding to that, it is asked that you need to calculate the length of the pipe for given pump. Okay, so you have pump, you have to just test that how much length this pump can provide the flow of the fluid. So it means you need to determine simply the length of the pipe. So this is also a very simple problem because your friction factor is only dependent upon Reynolds number and roughness. These are given parameters. So you can calculate Reynolds number, calculate friction factor, and simply calculate the value of F. Now third type of problem can be where in the question head loss is given, density, viscosity is given, length is given, diameter is given, but discharge is not given. So if discharge is not given, in that case, what is the difficulty? If you have to apply the head loss formula, H equal to FLV square by 2GD, you need to calculate the value of F. And for calculating value of F, you must know the Reynolds number. And Reynolds number involve rho Vd by mu, but V is not known to us because velocity or discharge is not given. Okay, so what to do in this scenario? How you can apply Bernoulli if nothing is given? So regarding discharge, there is no information. So what you will be doing in this type of problem? So this is where the difficulty comes. So what we need to do, there are two ways to do that. First way is follow the iterative procedure. Okay, we will be assuming some value of, we will be guessing the value of discharge. Corresponding to that guessed value of discharge, we will be calculating Reynolds number. Corresponding to that Reynolds number, we will be calculating friction factor. We will be substituting it into our head loss formulation, and we will be calculating the corresponding value of new velocity. Then with reference to the new velocity, we will get another Reynolds number. We will check whether my new Reynolds number, whatever friction factor it is giving, is it equal to the previous value of the friction factor. If it is equal, my solution is converged. If it is not equal, then I have to judge whether I am on the higher side or on the lower side. If I am on the higher side, then I have to decrease the value of flow rate. If I am on the lower side, then I have to increase. Okay, and once again, I need to do this iterative procedure unless or until my value of friction factor converges. Are you understanding this point? So this is the iterative procedure. Iterative procedure is good for theoretical computations, or if you are taking the help of computers, etc. But if you are on, say, in some plant site and you have to immediately calculate the value of pressure drop, then this will become little cumbersome. Okay, so that's why by taking the help of dimensional analysis, another procedure was developed, and this is what which I have shown over here. Okay, so what is done basically, we are having how many parameters? HF, L, D, rho, mu and V. Either V or flow rate Q. You can take any parameter. Okay, so both are fine. So if I have these many parameters, if I consider repeating variables to be rho, mu and D. Rho, mu, D I have considered as the repeating variables, and then I have performed the dimensional analysis. By performing dimensional analysis, I will be finding one function zeta is equal to function of Reynolds number, where zeta is nothing but GD cube HF by L nu square. So nu is nothing but mu by rho, and this comes out to be F into Reynolds number D square by 2. So this particular data of zeta is correlated with Reynolds number from the experimental measurements, and it is found to be 1.75, but particularly when Reynolds number is less than 1E5. Okay, so once you know the value of zeta, which is simply a function of Reynolds number, you can substitute back to get the value of F. And when the wider range of Reynolds number is chosen, then this is the correlation. How this correlation can help us in finding the value of Reynolds number, you can clearly see this zeta is becoming independent of the, does it have any inclusion of velocity of the flow? Velocity of the flow is coming over here? No. So velocity is not coming into this picture. So if velocity is not there, zeta can be calculated by knowing the other given parameters. Okay, so by knowing other given parameters, because HF is known to us, L is known to us, D, rho, mu, all are known to us. By knowing these parameters, only unknown is velocity. So by knowing all these parameters, I can calculate the value of zeta, and if I substitute zeta over here, then I can calculate the values of Reynolds number. And once I know the Reynolds number, then I can directly calculate the friction factor and substitute back into the equation FL V square by 2 GD equal to HF, and I can calculate value of velocity. Okay, for wider range of Reynolds number, so this first relation is applicable only for Reynolds number less than 1E minus 1E5. For wider range of entire range of turbulent flow, this is the more generic correlation. Is this point clear? So this is nothing but a deterministic approach to calculate the velocity if it is not given for a pipe flow problem. Okay, so what I will do, maybe I will give you some assignment, and in that assignment I will include this type of question, where one time you have to calculate it by iterative procedure, and second time you can calculate it using the deterministic approach. Okay, then we have fourth type of problem. In case of fourth type of problem, what we need to do? Now situation is slightly different. Now we have, out of all the parameters HF, L, V, rho, mu and D, all these parameters are known. So these are known parameters, but unknown is diameter. Okay, diameter is unknown parameter. So when diameter is unknown parameter, then what will be happening? Once again, there is difficulty that we cannot calculate Reynolds number. If we cannot calculate Reynolds number without knowing the diameter, I cannot find the value of friction factor F. Okay, so here also I have to follow once again the iterative procedure. Now along with the iterative procedure, people have also tried to apply some approach of dimensional analysis so that they can come up with the deterministic approach, as was shown in the previous slide for the case of unknown discharge. Okay, so here what people have done, first Reynolds number is presented in terms of flow rate, rather than velocity, it is presented in terms of volumetric flow rate. Okay, and then volumetric flow rate, rho and mu, these are taken as repeating variables. By considering these repeating variables, we get Reynolds number is equal to function of some one non-dimensional parameter into the second non-dimensional parameter. Okay, but it is important to mention that though we got this functional relationship, but there is till date there is no exact correlation known between these dimensionless groups. So it means when the problem comes to estimate the diameter of the pipe, in that case you cannot follow any deterministic approach, though we are having existence of dimensionless parameters, but till now there is not enough data so that exact correlation can be made to relate these dimensionless parameters, and you can have some deterministic approach with the help of which you can calculate the values of Reynolds number for your calculation of friction factor. Okay, so that's why in this approach one has to go for purely for the iterative procedure. Is this point clear? Okay, now okay, we'll discuss in the next class.